All right, it's 11:15. Before we get started, does anybody have any questions about what we've done previously? Do we understand what's due coming up soon? 1.3, when's that due? Tonight, right? So yeah, it's tonight at midnight. Most likely that means 1.4 will be due on Friday night. We're gonna finish it in the first half of class today. Also, your first quiz, I'm gonna post sometime today. That'll be due on Monday. And like I said, it'll be due Monday at 11:15. You can either turn it in to me physically or you can put it on Canvas. Either one of those things is fine. The first quiz. So there's a space for it on Canvas right now. I will write it up sometime today. So I'll have a pretty good idea where we're going to end the week by the end of today. All right, so if there are no further questions, let's go ahead and get into it. So we're still in 1.4, finding limits, and pretty much up to now, the bulk of our work in finding limits, calculating limits, has been kind of a systematic guess and check, where you're taking values very, very close to your base point, your base number, and seeing how the function behaves. So let's look at something where we can be a little more sophisticated in doing that. So I think this is the exact same function we've looked at before, where we actually just guessed a few values close to 1 on either side. And I even think when I did it that day, somebody suggested something a little more efficient and effective. Do you remember what that was? Not straight away, but we can work up to that. Yep. So let's do that. The numerator here factors into the product of x plus 1 times x minus 1, all divided by x minus 1. Now I have multiplied factors, so now I can truly cancel, and I get this. Limit as x approaches 1 of x plus 1. Which, to put a really fine point on it, like we did last time, this is equal to this, right? The limit as x approaches 1 of x plus the limit as x approaches 1 of 1. Which ends up being 1 plus 1 is 2. So obviously preferable and more to go about it that way than show me a table with a bunch of guessing and checking that you've done. And I made this point last week, but I think it's worthwhile to revisit it, because it is tempting to believe that this is true. But remember, that is not true. And why is that? Why can I not say that those sides are equal? Right. So, why did they want 1 over x plus 1? Now that I've written that correctly, is that equal? Still no, because the right-hand side is defined at x equals 1. The left-hand side is not. So they have the same limits at x equals 1 and everywhere else, but they are not the same function. Any questions here? So factoring, definitely gonna come up. I'll just make a note here, because this is a pretty common technique for algebraically finding the limit. All right, how about this one? Got a piecewise function. So when x is not equal to 1, my function is equal to x plus 1. When my x is equal to 1, then the function is evaluated at pi. So what is this limit? The limit as x approaches 1 of my function g. Is it pi? Is it 2? Is it something else? Got 1 vote for pi. Anybody else? Maybe it would help. We got 1 vote for does not exist. So let's draw a picture here. So 0, 1. Then that line is straight. So I got a discontinuity here. And when x equals 1, I have the functions equal to pi. So there's what the graph looks like. Does the graph change any of your thinking about what the limit might be? Someone's saying 2. So remember, and this is kind of the thing I've been harping on for a while now, is that the limit of the function has nothing to do necessarily with how the function is evaluated, like what value the function takes at that point. So I know that, let's just kind of break this down because this is an important thing to look at. The limit as x approaches 1 from the left of this function is 2, right? I mean, as I pick x values that are below 1, but very near 1, I'm getting closer and closer and closer and closer to 2. You can say the same thing on the right, correct? But what is this equal to? 5. But that's okay. This limit is equal to 2. So and if it helps, I mean, it'd be great. It would save you time if you could look at this two-sided limit and kind of visualize it from both ends and see that the limit is 2. But if you need to break it down and approach from the left, approach from the right, see if they agree, it's totally fine. Especially for, I suspect some of you, this is your very first time seeing limits, especially in this detail. So I did get some votes earlier for the limit does not exist and the limit is pi. We understand why those two things are not the case. And like I don't know if I stressed this last time, but if you have questions, stop me. We have time. All right. How about this guy? Clearly, I cannot rely on what the value of this function is when h is equal to 0. This one might be a little more cryptic as to how we attack it. Anybody have any ideas? Good. Okay, we got 1 vote for doing this. The limit as h approaches 0 of 3 plus h squared minus 9 divided by the limit of, as h approaches 0 of h. How do we feel about that? For me to use this limit law, what has to be true? So yeah, so 3 things I have to look at here. The limit of the numerator has to be well defined. The limit of the denominator has to be well defined. Those are both obviously good. I mean, the top is a polynomial, and the bottom is a polynomial, and I kind of gave you for free last time that if you have a polynomial, then you can really just, they're continuous everywhere. The limit's defined everywhere. You can just plug in whatever the base point is. But I do fail that third condition of my denominator having a limit of 0. So I can't really do this. Any other ideas? Go ahead. When you say factor out, the opposite of factoring, we're going to distribute. Yeah. No, it's fine. I mean, and those 2 things are really opposites. Factoring and distribution are, I know they're things you both know you know how to do, but yeah, they're opposites. So yeah, let's try that. So we can't really use that, but I'm glad it came up. Go ahead. Oh, is that what you're saying? Okay, I didn't see it that way, but yeah, I think those are, yeah, if you look at the numerator as a difference of squares, that'll work too. So in fact, let's do both. So quickly expanding that bracket, I'm gonna get 9 plus 6h plus h squared minus 9 all over h, or if we factor, we get 3 plus h minus 3 minus 3 plus h plus 3. I did something wrong, didn't I? It should not be subtracted, but okay, that's what I want. All right, I'm gonna deal with this top one first, or did somebody, I saw a hand out of the corner of my eye. Okay, and I'll tell you right now, I have looked at a lot of things like this. I've never seen, I would not have foreseen this bottom approach, but I'm glad it came up. So this right here is equal to the limit of h squared plus 6h over h. Budget my space enough for this one. I believe this left hand, kind of this bigger bracket, just becomes h, right? So do we agree with this? So this is the limit as h approaches 0 of 6 plus h, which you will probably recognize that the one up top will do the same thing. If I factor out an h. Is 6 plus h a polynomial? It is. I mean, it's a pretty simple one. I'll remind you of what the true definition of what a polynomial is in just a bit, but yeah, it's a polynomial. So I can kind of take, it's not really a shortcut because once you understand that it's totally valid, just substitute in there and I get the limit of 6. So we saw a couple different algebraic approaches there. They're both good. They both end us, both get us to the same result. But just one more caution, and this is going to come up a lot. I'm not picking on anybody. I just, man, I had one person bring that up, and I would bet money that other people were thinking it as well. But those limit laws, make sure you're allowed to do them. If you're allowed to use them. Any more questions on this example? Yay. So squaring something is a much different thing than that square root. Clearly, I can't just plug in, so a couple things. I can't just plug in 0 for t, but I also can't rely on that polynomial property anymore. You have an idea? Just the way that I typed it in. No, I mean, those are both fine. Yeah. So, and really, most times when you're writing it out by hand, you'll put the base point right underneath. Sometimes, I don't know why Word and PowerPoint decide to leave it off to the right, but you'll also see that done. They're both totally fine. Okay. This one, any ideas how to deal with this one? This is a little more mysterious. And that's what I was looking for. So this idea of a conjugate. So you say the conjugate of the numerator. What would the conjugate of this numerator be? There you go. So basically same two terms, but I'm going to invert the sign between. So let's start with what I gave you. Radical of t squared plus 9 minus 3 over t squared. But then I'm going to multiply this function by this very strange expression of the number 1. Square root of t squared plus 9 plus 3 over square root of t squared plus 9 plus 3. I want to pause there because I'm not gonna assume that all of you have seen this approach before. Those of you who have seen this, what's the goal of doing this? Right, and I kind of want to unpack that a little more. When we say we're simplifying, what is it we're trying to make simpler? Yeah, we're trying to clear that radical from the numerator at the penalty of putting a radical in the denominator, but maybe that'll be okay. And the reason we do the conjugate is if we have 4 terms here, which you would think we'd have to go through the motions of getting all 4 terms for, but hopefully you see that the middle terms are going to come from 3 times the radical and negative 3 times the radical. They cancel out. So really what I'm left with the numerator is t squared plus 9, and then negative 3 times positive 3, which is 9, or negative, all over t squared times t squared plus 9 plus 2. All right. I think so, because that 9 cancels with that negative 9. T squared over t squared times radical t squared plus 9 plus 3. All right, and even though I don't have a polynomial or a rational function here, I will spoil some things for myself and say that this is one of those cases, and I'll go into more detail about why this is one of those cases where I can rely on continuity and just substitute in my value. So in this case, this new expression is defined when t equals 0, so I get a limit of 1 over 6. Go ahead. Is it not? Oh, sorry. Now you can just plug in basically 1 over radical 9. I believe that's, yeah, let me know if I made a mistake. But I think it's 1 over 6. What happens to the t? You just have to follow order of operations. So first, yeah, square 0. Basically, you're taking the square root of 9. Yeah, I mean, so that's an important thing that I don't. You have to make the value very, very close to 0. So yeah, in the end there, when I'm substituting, I'm going to substitute 0 into t. Good question. Anyone else? All right. This limit here showed that this thing does not exist. So I got the absolute value of x over x. So why might a limit not exist? Okay, so you might have the one-sided limits are different. Anything else? We've seen other reasons why a limit might not exist. What? That alone isn't enough because we just saw an example where the denominator was 0 and we found the limit. So that is a problem. I don't think it's a showstopper for why a limit might not exist. But one example I'll just put off in the margin here. Now, if you have something like this, so that I think we've looked at this exact function before. Maybe it was 1 over x squared. But that limit doesn't exist because I can make this function as large as I want by getting closer and closer and closer to 0. So there are a few different ways where a limit might not exist. How does the absolute value function behave? Turns negative to positives. What does it do to positives? Yeah, it just passes that value, right? So one definition of absolute value that you've probably seen, but it's probably been a while, is this. The absolute value of x is equal to x when x is greater than or equal to 0. And it's equal to negative x when x is less than 0. Which really is what was just described. It's going to take any negative value and return a positive number on the other side of the 0. So I think a lot of these things are helpful to break down by graphing if you can do it somewhat easily. And this one is a little more straightforward than, for example, the last one we looked at. But if I wanted to look at x versus the absolute value of x, you're going to see something like this. Straight line on either side that has that hard cusp at the origin. So based on that, can we generate a graph for this, the absolute value of x over x? So I think we know that this graph can't be defined at x equals 0, right? What's this graph going to look like for positive values of x? So it's going to be a constant straight line 1, right? Should have made a solid dot there. So this level's 1. How about in the left side of the y-axis? Not nothing. Negative 1. Oh. So again, not defined there. We have a graph like this. So now that we have the graph, we have a better idea of what that limit is. What is it? It does not exist. So, I mean, if you want to, you're really convincing about this, you could say this: the limit as x approaches 0 from the right, this function is different from the limit as x approaches 0 from the left. Does the fact that this function is not defined at 0, is that a good enough argument? No. Yeah. So yeah, that's not a good enough argument. We just looked at a few examples where our function was not defined at the point that I was interested in, but I still had to look. Any questions here? All right. Next example. This strange function. Limit is x approaches 0 of x squared sine of 1 over x. So clearly x squared, that's a polynomial. I know that will have a limit no matter where I look. How about sine of 1 over x? If this was sine of x, could I figure out what the limit was as x goes to 0? Right, that's pretty simple, right? But what happens to 1 over x as x gets really, really close to 0? Gets larger and larger, right? Can you take the sine of a really, really large number? What's the sine of 1,000? I mean, I don't really need to know, but just to know that it exists, right? I mean, trigonometry is all cyclical, so if you take the sine of any number, you're gonna get a result back. But what happens when if you try to plug in 0 for x with this function? That's not going to work because 1 over x is not defined, so your sine cannot be defined. But I am telling you that this limit exists, and I show this to you knowing that we don't really have the know-how to deal with it, so we got to introduce something new. It's called the squeeze theorem. So let's say that I have 3 functions. So 3 functions f, g, and h, where you kind of have this tower. F is less than or equal to g, which is less than or equal to h, in some vicinity of a, in some neighborhood near a. The other thing I want to assume is that the limit as x approaches a of the 2 outer functions, the least and the greatest, that limit's the same. So if I have f is less than or equal to g, which is less than or equal to h, everywhere in that kind of neighborhood around a, and I know the limit as x goes to a of f of x is equal to the limit of h of x, what do you think that means for that limit of g? I'll try to draw a picture here. So here's A, and I have, here's L. L. So I have these 3 functions, f, h, and then g is kind of sandwiched in the middle. So g is in between the whole time. I know that the limit is of f and h, those are both L, right? So what do you think the limit of g of x is at the same place? L. So basically, this is what this theorem does. If I can find these other 2 functions that kind of trap the one that I'm interested in, I know it has the same limit as well. Yeah, and this is a kind of a complicated thing. And hopefully when I show you an example, it'll become a little more intuitive, but let me label these functions actually. I said the least of them was f, greatest of them was h, and the middle one was g. So here are the things that I'm telling you for free. F, g, and h are functions, and they kind of have this ordering. F is less than g, g is less than h. Go ahead. What do you mean by always be like this? Yeah, really, I mean, I've seen this theorem where they're named different things or they're named in the opposite order, that's fine. As long as you have, one function that's the least, one function that's the greatest, and then one that's strictly between them, you're fine. Shouldn't say strictly between, they can be equal. So I'm giving you that for free. I'm also giving you for free that for some number a, the limit of f and the limit of h is the same. If you meet those 2 conditions, then I can also guarantee that the limit of the middle function is the same. Hopefully that made it a little bit more clear. Hopefully it makes it even more clear when I give you an example of this. We're going to revisit the one we just looked at. So back to this guy. So clearly we know the x squared part of this is not the issue. It's really this sine of 1 over x. So let's think about the way the function sine behaves. So here's what we have. We're going to call g of x this. x squared times sine of 1 over x. Because that's the one I don't understand. That's the one I'm going to try to find two other functions, one smaller and one less, or one smaller and one greater, that I can kind of encapsulate this other one. So let's think about what we know about the sine function. Does the sine function have a minimum and maximum? Not 0 and 1. Close. -1 and 1. So here's what I'm going to do here. I know that, no matter what value of x I'm dealing with, the least that sine of that number can be is -1. So I'm going to call this function -1 times x squared. I'm going to call this function, what's the greatest thing sine can be? Just 1, right? So this is going to be sine of 1 over x. Oh, whoa, what am I doing? 1 times x squared. So my f and g functions are things I really understand. Are f and g polynomials? Yep. So I really know a lot about those. So I'm going to go ahead and graph them. F looks like this. H looks like this. And since f and g are polynomials, what do I know about the limit as x approaches 0, both of those functions? Those are 0, right? So let's see if I met my conditions. I actually didn't graph. And this G1, it's going to look a little strange. It has a sine component to it, right? So it's going to, and this is kind of a guess, it's going to look something like this. It's going to oscillate indefinitely. But I know that, we understand that sine is between -1 and 1. So there's no way that G function is ever going to escape like that envelope with those two parabolas. So I'll remind you of the two conditions again. So I have three functions where f is less than g, which is less than h. So that's one condition I met. Do I have that the limit of f and h are equal to each other? Yep, they're both 0, which means that the limit of the middle function g has to be 0. So kind of a strange thing. There's a homework on WebWork to get more practice with that. But yeah, if anybody has any questions right now, let's talk about it. Or if you have questions about it down the line, ask me. Go ahead. We proved the limit of that strange function I gave you is 0, right? Which I don't think can be done without this, because you have a function that's not continuous at the point that I care about. Yeah, it's a little hard to contrive something on the spot that works with this, but let me make a note for myself, and after class, you want me to send out a worked example for everyone, or do you want me to send one out that you can just tinker with? Okay, I'll send it unworked, and then if people have questions, I'll work it out myself. Yeah, I mean, which is essentially what we did here. But if you want to graph it, then are you just talking about graphing G or graphing all three of these? Right, right. I sort of think that if you try to graph this on a graphing calculator, it'll be a little strange to deal with. I could be wrong, but I think if you put sine of 1 over x in a graphing calculator, you can get closer and closer and closer to x, but it still is not very convincing. I could be wrong about that. It's been a while since I've actually tried to graph that. You can? Okay. All right, anything else? Okay. So that is the end of 1.4. And I keep using this word, and I finally now get to talk about what it means. Continuity. All right, I think everyone's heard the word, but maybe you don't have like a rigorous definition squared away. Does anybody know what it means if I say a function is continuous? Anything at all? Go ahead. Okay, it goes on forever. It's infinite. No discontinuities. Anything else? I mean, it's one of those words I probably heard in every math class you've ever taken, at least for the last several of them, but maybe you don't have that technical definition. So let's either remind you of it or show it to you. So the first flavor of continuity I'm going to show you is a function being continuous at just one point. And we're going to extend that from there. So a function f is continuous at some point a if, and this is the definition, if the limit as x approaches a of f of x is equal to f of a. So I'll unpack that a little bit, but this is really the bottom line. So if we unpack it a little bit, there are a couple things that are kind of hidden in there, a little more shrouded. So in other words, f of a is defined. So, for example, we looked at a lot of limits just a few minutes ago where my function was not defined at some point, but the limit still exists. So the limit might exist, but those functions were not continuous at that point. So I need to have my base point a, that needs to be in the domain of my function. F of a needs to exist. It needs to be well defined. So f of a needs to exist, and also the limit as x approaches a of f of x needs to exist. And finally, they need to agree. So we've seen lots of examples where the limit exists and the function is defined there, but they don't agree. That's a discontinuity. We've also had examples where the function is not defined at the base point. That's a discontinuity. And it's kind of the most basic, like the first failure you can have is if the limit doesn't exist, then you definitely have a discontinuity. Just for my curiosity more than anything, is this brand new to most of you? Okay. And it's one of those things that really until now, there's not a huge push to really get into it. But now we're going to need this precise definition. Any questions on the definition? Okay. Times after class. Last time, the notes are there on Canvas ahead of time. You're totally fine to look at them ahead of time. It's not required at all, but they're there if you want to take a look at them, print them out, whatever you want to do. I wouldn't recommend though. I've always posted notes after I've made all my annotations on it in class, so I would recommend going to Canvas to get those. All right. So let's look at an example here. This is a function we've seen before, but let's apply those definitions here. So given this graph of g, I want to know all those values of x where this function is not continuous. Go ahead. Why is it discontinuous at x equals 2? Okay, that's one reason. Or both the points.
I don't know, it has holes at the value.
Okay, so I'm going to write that this way. G of 2 does not exist. Is there any other justification you could have given for x equals 2? There's a jump, so yeah, or sorry, we're looking at x equals 2 still, I'm sorry. But yeah, there is another reason I can give for why it's not continuous at x equals 2. Go ahead. Limit does not exist. So the limit as x approaches 2 of g of x does not exist. Because the one-sided limits don't agree with each other. So both of those, I don't need both of those. Either one on its own is fine to tell me why there's a discontinuity there. I have at least one more. X equals what? 5. What's a good reason for that? There's a hole. Can I mathify that up a little bit? Yeah, you know what you're looking for. That's step 1. Yeah. Yep, that's perfectly said. So the limit exists. The function is defined there, but they do not agree. Are there any other discontinuities on this graph? That's a complete list. As far as we can see, x equals 2, x equals 5. Any questions about this one? All right, now let's look at a function where I'm looking at the definition of it, but not a graph. Where is this one discontinuous? Okay. X equals 2. Can we give a good reason? Right, f of 2 doesn't exist. And that's enough. I mean, so I gave you those. Really, there's one condition, but you can kind of break it down into those 3 like little smaller things. If any one of those fails, then we have a discontinuity. Question? How do we know that was x equals 2? Can divide by 0, right? So a couple things here. Without really, analyzing this algebraically, I don't know if I have, this continuity could look like at least these 2 things. You could have something like this, where there's just that kind of discontinuity, or you could have something like this at x equals 2, where without really getting into it, we don't know what we have here, but we can tell just from the way the function is defined that when x equals 2, there's no corresponding. Are there any other discontinuities here? What kind of function are we looking at? It's a rational function, right? And I think we talked about this a little bit on Monday. Today's Wednesday. Where are rational functions defined? Maybe let's back it up a step. Rational function has polynomial in the numerator and polynomial in the denominator. Where are polynomials defined? Or where are they continuous? I guess I've only told you where they're defined. Is there any number I can't square? Nope. Is there any number I can't subtract by some other number? Or they're subtract by 2. So I mean, you can't really, there's no way a polynomial can be undefined. You know, you're just raising numbers to powers, adding and subtracting them. Polynomials are defined everywhere. So the numerator and denominator by themselves are defined everywhere. So what's the only way a rational function might not be defined somewhere? If you end up with a division by 0 situation. So that's the only place where we're gonna see a discontinuity for x equals 2. All right, this guy here. Where is this function discontinuous? Okay, so discontinuous. We have x equals 0. Why is that the case? Yep. Okay, so what is 1 divided by 0? Can't make sense of that, right? So really what we have here is, you know, the limit as x approaches 0 of 1 over x squared is not equal to f of 0. So that's enough. What is the limit? I got to vote for 1. I got to vote for 0. It's infinity. So yeah, remember the limit and what happens to f is it?
That has to be written as the limit is undefined.
Yeah, you could also, or yeah, you could absolutely.
What specifically answer.
No, that's true. Yeah, so the infinity is just a way for me to be specific about the way in which it fails to exist. And last question I want to answer before I send you out is this: where is this function defined? Everywhere. So, you know, it fails to be continuous at that x equals 0, but if I just had f of x equals 1 over x squared, it would be defined everywhere except for 0. But since I amended that to say 0, 1 is a point here, it's defined everywhere. All right, everyone, keep an eye out for a new web work due date for Friday. And the first quiz will be up sometime this afternoon. I'll stick around for a bit if anybody has any questions. Hey there. Sure.